Great. Okay, thanks very much. So yeah, we're moving a little further south, but still partly within the Arctic. And I wanted to introduce you to some of the work that we've been doing in the Norwegian Sea, the deep part of the Norwegian Sea. Let's see. Yeah, so this work is part of the Mariano program, a deep sea mapping program funded by the Norwegian government to map the offshore area. This is a multidisciplinary program aiming to deliver data and maps on the bathymetry, the geology, the biology, and the environmental status of Norwegian offshore seabed areas. So it's ourselves at the Geological Survey of Norway in partnership with Kartverket, which includes the Norwegian Hydrographic Office and the Institute of Marine Research, focusing on biology and some of the chemistry. And we're aiming basically to map everything we find. We're not targeted on research. We're basically a baseline mapping of the seabed and delivering information for management and various other user groups. Norway's Mariano has been going since around 2005, initially focusing on the shelf areas. So this gray area is considered fully mapped now. There's some other areas in progress. But our focus is now shifting towards the deep sea. And this is this area, this area is far from being a featureless deep sea abyssal plain. It contains the mid-Atlantic ridge, which you'll see on all global bathymetry data sets running up here. We've got the Molloy Deep up here, which extends down to 6,000 meters. And various seamounts and many other things that we know relatively little about. So along the ridge, of course, we've got deep sea vents, images, something like this. There's only been a few investigations so far, so there's very little very much we still don't know. And we really need knowledge of this deep sea area to update management plans. Of course, there's renewed interest, very much interest in deep sea minerals. There's unique and vulnerable ecosystems. There's a huge range of geo and biodiversity, and much that we don't know. The Mariano program, we've been tasked with mapping this area, but even with a well-funded program such as Mariano, we can't map everything. So we tried to map what we have hopefully are representative areas of this huge deep sea territory. To decide where we should focus our efforts, we did some kind of unsupervised classification using bathymetry and oceanographic data. And we supplemented that with some expert-derived knowledge. So the classification in itself was not quite enough, and we focused our efforts along these areas to come up with 40 representative boxes. Most of these have now been mapped using surface-based multi-beam bathymetry mapping. This was carried out in 2019. So all of these small boxes you see in the color have now been mapped at somewhere between 10 and 25 meters resolution with regards to bathymetry. It looks very small area relative to the total area, but we've mapped in total 64,000 square kilometers across these 40 boxes, and each box is roughly 35 by 35 kilometers in dimensions. All these data are pooled together with any existing data. There are some older surveys, generally a little worse quality than the new data from surveys conducted in connection with the Law of the Sea surveys back around the sort of 99 to 2000 time. And all of these data that we acquire in Mariano are fed on further to regional data initiatives, including these and Seabed 2030 and incorporating the IBCO data set that we heard about in the last presentation. So that's the background, basically. Just to give you a flavor of the quality we can expect from these deep sea surveys. So this is using a relatively low frequency echo sounder, reaching down several thousand meters. You're working from a surface vessel, so the boat is rocking around. The data are corrected for motion artifacts, but generally we often find that these corrections are a little imperfect. You can see some striping, hopefully, in this image. And these are quite typical sort of multi-beam artifacts, and also some corrugations along track. So here we see the survey has gone in a different direction. You can see those corrugations. I don't have time to go into the details here, but if you want to learn more about artifacts typical in multi-beam data, I recommend this article by John Hughes Clark, which featured in our special issue on marine geomorphometry a couple of years back. And of course, artifacts such as this have consequences when you want to derive terrain attributes. We'll see some of those pop up as we go through the presentation. I mentioned the extreme depths we've got in the Molloy Deep. So here we're nearly at 6,000 meters depth. For some reason, it seems to be harder to visualize negative terrain, extreme terrain, than mountains sticking up high. But as you see, this iconic mountain Stettin in Norway, only just over 1,000 meters high, is absolutely dwarfed by the Molloy Deep at 6,000 meters, and a much bigger area covered by that. So that's just to kind of orientate yourself. And we found when we started to dive into terrain attributes and things, it was very useful to get a hold on what happens on land too, so that we can picture what sort of terrain we are coming across. So first thing to show you the relative relief. This is a quite common metric in nature type mapping or habitat mapping within Norway, particularly both on land and underwater. And simply it's the depth range within a 1 kilometer area. You could pick any other region, but the standard in Norway is 1 kilometer squared. And this gave a very useful context to how extreme the terrain we're going to encounter in the deep sea is. So I don't think many of you would think of Norway as a flat country. Here we see an image from Jotunheimen, which is a region that contains Norway's highest mountain on the mainland. And we're getting relative relief values up to around 700 or 800 meters here. In contrast to that, along the mid-Atlantic ridge and those areas, we're easily seeing values well over 1,000 meters. So very, relatively over small distances, the depths are changing pretty rapidly. Okay, so why do we want to know this? Well, we don't just map bathymetry, as I said, we need to map geology and biology. We generally do this from a surface vessel. We use towed video cameras. We send grabs and other equipment down to the seabed. All of these have to go up and down and be as cost effective as possible. As we move to the deep, of course, the up and down from the ship takes longer, and we need more, rugged and tough equipment, possibly. But imagine, you want to either have some kind of towed equipment, like a remotely operated vehicle, or this, which is a kind of combined remotely operated vehicle which lives inside here, and some grab samplers. Imagine dangling that down on a cable from the ship, which is swaying around in waves, or sending off an autonomous underwater vehicle into this terrain, which is pretty rugged. You kind of want to know what terrain is there and what you can trust, and what's the limits of operation before we plan the follow-up surveys. So how can we use terrain attributes to help us decide what equipment we can use where? That's kind of the focus of what we're working on right now. Obviously, we will use terrain attributes also in follow-up geological and habitat mapping, but this is where we're at right now, trying to figure out how to plan those follow-up surveys. So which attributes are most useful to us? What scales is it most useful to plan and have information? That kind of questions that are coming around now. So for the rest of the talk, I'm going to focus on two example boxes that we've been using in planning. They've got similar average depths, but they're very different in terms of the complexity. So at the Mid-Atlantic Ridge, we've got this site here. Huge variations in terrain, very rugged, and the relatively flat site, which still contained some mounds and craters, which we'll see contrast quite sharply with the other box. So relative relief now calculated on the local bathymetry, so a 20-meter bathymetry grid. So you should say the previous one you saw was calculated on a 100-meter grid for the whole area. So here we're seeing, again, extreme variations and really very little happening in the flatter box. Yeah. Moving on to slope. This I'll show you at, we kind of focused on sort of intuitive analysis distance, adapting the number of cells used for the focal neighborhood to something that people planning surveys who are not used to terrain analysis can get their head around. So an analysis distance of 100 meters first. We see that we're finding in some places slopes up to over 70 degrees and very relatively low slopes in the flatter area. Of course, when we move out to a broader scale slope over longer analysis distance of like up to 1 kilometer, these slopes, as we've seen many times before, broaden out, but they're still pretty high. They're still over 40 degrees in certain places. Yeah, and ruggedness, or yeah, not ruggedness, sorry, local topographic position. Here we've tested a number of measures. Here you're seeing the difference from mean elevation as calculated in white box tools. This is very similar to the bathymetric position index or topographic position index. BPI is used very much in marine applications, partly because it's included in the benthic terrain modeler toolbox for ArcGIS, which is very widely used. So it's just the neighborhood that changes in this analysis. We did run this also at finer scales, but mostly we find it captures noise and artifacts. So the broader scales are much more useful in this context. And you see sharply again the contrast between the two areas here. What's nice about this is also that you get, you know, these values are actual meter values, which can be, you know, an ROV operator could relate to, that kind of thing. We've looked also at some alternatives using relative local topographic position metrics, which various authors have claimed are more suited to geomorphic analysis and that kind of thing. We agreed to a certain extent that they pick up certain features, but we also notice, for example, in this figure here with the elevation percentile, it also seems to pick up those artifacts, if you remember, that we saw in the data. So that's not necessarily a good thing. Similar story here in the deviation from mean elevation here and the RTP index. Whereas the absolute LTP using the difference, that seems to not have that similar problem. So it's a case of balancing what you want out of these analysis and what kind of values you need. To also these other metrics, they're a little harder to interpret in terms of intuitive values. But I'm certainly not dismissing them, but just for the purposes of planning follow-up surveys and where you can go with different equipment, then it seems like this is a good bet. We've looked also at the multi-scale roughness. This has been introduced by a number of authors. Vince LeCour had a nice presentation the other day looking at using this in very shallow waters. So I won't go into background, but of course, this is based on the dispersion of the surface normals. So in the rugged area, we're getting much more dispersion, and the flatter area, much less. We see also the accompanying scale of maximum roughness. Generally in this rugged box, we're seeing broader scales dominating, at least medium to broad scales. And where we happen to see the finest scales dominating, that tends to be in areas of very low roughness. And that seems to be linked with artifacts in the data. On the other side, again, we see some striping in the scale output, which again is linked to the artifacts in the data, which you don't see in the values because I've used the same color scale on as for the deep area, for the complex area in each case. We have tested various different filter distances, but again, we've stuck with this 1 kilometer, which seems to be relevant to the operations of the underwater vehicles. Okay, we tested also various other metrics for roughness or ruggedness. I see these cropping up in a number of the talks over the last few days. So it's good to see there's possibly a few more we should be testing. Vector ruggedness measure is very much used in marine applications. Again, it's included in this BTM toolbox. It's relatively widely accessible through a number of softwares. We have found that it tends to be prone to that you can see the effects of the neighborhood, the analysis neighborhood, as you move to broader scales. And a similar case for the standard deviation of slope, which also has been proposed as a measure of roughness. But obviously these have their place. So far, we kind of like the output from the multi-scale roughness, but especially in talking to people who are less familiar with terrain analysis and things, it can be difficult to get your head around having these two outputs. And we're wondering if there's some way you could combine those outputs to make it easier to interpret for non-specialists. But that's kind of an open question. I'd be interested to hear people's thoughts on that. So yeah, that's pretty much all I've got time for. Certainly, we see that terrain attributes are useful for quantifying the terrain. And so we can characterize it with actual values. We tend to find that we want an intuitive metrics with a kind of tangible value, so that we can plan these underwater operations. And the next step is to talk to the operators of these underwater vehicles to find thresholds for where they think they can safely operate their equipment. Sometimes it will involve doing an underwater higher resolution acoustic survey before we actually go close to the bottom. Yeah, so there's plenty more to do. We will be also interested in fusing this new information in a better way with regional data. And also, of course, the next stage is all the follow-up, the geological and biological habitat mapping once we eventually get to the bottom with our cameras and sampling equipment. So there's much more to come. So thanks very much for your attention. I'll take any questions if we have time. Thank you.
Sebastiano, you want to ask a question?
Yes. It's more a suggestion in regard to roughness measures, because for example, I remember the papers of Earthfeld of the 90s of the past century. She started to apply geostatistical based roughness indexes to bathymetric data. From then, there was a lot of work both in remote sensing as well in geomorphometry. And for example, yesterday I was talking about the algorithm that we developed that is a robust version of variogram and is used for multi-scale analysis of roughness. And I know that has been implemented in the Bentic software, I think, from Esri, that is directly used for bathymetric data. And from the point of view of the interpretability of the result is very simple, because at the end you are evaluating the roughness along different direction and a specific scales. And from the basic indexes, you can also build more complex indexes. You can also develop approach similar to the one of Lindsay with multi-scale roughness. So it's very easy to build more complex stuff from simple ones. So I can send you some details if you are interested in this kind of approach.
Yeah, absolutely. Thanks very much for the tips. I'll follow up with you afterwards. Yeah.
Okay, I think we're running later and later. So we have our last talk of the morning before we get to the business meeting. I believe it's Guerrero et al. Who are going to talk us about wind farms and the geomorphometry that can work with them. So if you want to share your screen, please.
Yes, hello. Can you see my screen?
We can. If you want to, we're seeing the whole PowerPoint. So if you want to go to presentation mode.
Yeah. Okay. So as he said, my name is Caral Guerrero, and I'm from Spain. I work in a private company, which is Geociencias y Exploraciones Marítimas, also known as iGeotest. And I'm going to talk about marine geophysical investigation for the offshore wind farms and submarine cables interconnection between different areas. So here in the presentation, I'm going to start with an introduction to put in context the works and the projects that we are going to include in this talk. And then I briefly explain the most common geophysical methods that we use in submarine interconnections and cables projects. Then we will show some examples of the results obtained in one project. And then I'm going to show a summary of the talk. So here we can see a global map where we can see the huge amount of cables that are worldwide. So in the last 35 years, the seas and the oceans worldwide has been converted from to be clean of submarine cables to be built in an extended net of submarine cables. Most of them are related with the telecommunications. So nearly every corner of the globe is now physically connected. If we go to Europe, it's also the same line as the rest of the world. Specifically, the need of the marine electrical interconnections